All right, well, welcome to our first small group for W0TLM, and we're doing this as a bit of an experiment, so thanks for bearing with me as we give this a shot. I'm going to want to give credit where credit's due. Back in April, I attended a Rocky Mountain Ham University up in Denver. And there were a couple of presentations. And as I was sitting there listening to these, I thought, this could be the ideal first attempt at one of our small group meetings. There should be a little bit of interest in this, and it would be something that we could do via Zoom, which was kind of a requirement to be able to get people together, kind of off our normal meeting schedule. So two of the guys that presented, Ben Matthews, KC2VJW, and Willem Schroeder, AC0KQ, I have lifted some slides with their permission in this presentation. So as I mentioned, we'll give a little bit of background on SDRs, bits of information about the hardware that's available, cost, and then how kind of a basic how they work. There's a couple of really key things where you don't have to have a deep understanding, but it just really helps when you're hearing about this to have kind of an idea of what's being talked about. So SDR hardware, the easy mode. A bunch of people in our club already have this. The ICOM IC7300 is an SDR. It is an example of what's called a direct conversion SDR, and it is all self-contained. You don't have to have anything external to this to be operating an SDR. It is all built into it. But this is one of the, this is a more expensive way to get started in it, and you really don't get a chance to play with what some of the features are when you do it this way. But the thing that makes this a direct conversion SDR is if you look. Oh, by the way, are you able to see my cursor as I'm moving it around? I'm guessing not. Okay, so
there it is.
In the lower section on the copied page there, you'll see the receiver block diagram and the transmitter block diagram. See the receiver antenna, then you've got a box, the BPF, that's a bandpass filter. The next item is an A to D converter, and then an FPGA, a field programmable gate array. That is the crux of the signal processing that comprises the SDR. Actually, there's another box there, the DSP, but that is all in software. We're the filtering, instead of seeing a bunch of capacitors and coils and switches, that is done in software. And I'm going to show you a little bit about how that works in a little while. So this is SDR easy mode. Here's SDR hardware, slightly harder mode, but a much more expensive option, and that's a Flex radio. Here's a Flex 6700. The reason it's slightly harder is that you have to provide an external computer, because it's really just the radio conversion to create a digital signal that can be processed, that this box does, and then the actual processing is done in software that you run as an application on your desktop or laptop computer. We're not going to be going into this. Now, the SDR in even a harder mode is what we'll fool around with a little bit tonight. So these range from very economical to quite a few dollars. The pictures I have here, that one in the upper left-hand corner, the Rtl Sdr, the Rtl Sdr is what three of the demos I'm going to attempt tonight are based on. The SDR Play on the upper right is another box that I currently have running, and I use it as for rig control for my HF rig. So hopefully we'll get to see how that works. AirSpy is another relatively inexpensive. The Rtl Sdr is available for about $30. The AirSpy is probably around $100, I believe. The SDR Play is, I think they're running about $130, $150 today. The Hack RF1, I'm not real sure, but it's probably in that this same ballpark. There are a bunch of these. Now, the thing about them is that they all require integration with a software application to get them to work, and that's what we're gonna try and do tonight. Some other hardware considerations. The devices that I just showed you are receiver only. If we get into transmitters, we can do that in SDR, but that adds a significant amount of cost and not what I would recommend initially if you want to get started. Building receivers is interesting enough for the time being, and then you can always take that further later on. But like any other receiver, you need an antenna system if you're going to hear anything. External filters can be a good idea. And the reason for that is that these SDR devices have such a wide bandwidth. This Rtl Sdr that I'm using is from the kilohertz, I think 20 kilohertz, up to 2 gigahertz. And it's just a wide open receiver, and strong signals that come in, even if they're out of the band of interest, can pretty well block what you're listening to. So if you're in a real high area or a high RF energy area, like near a broadcast antenna, you may need a bandpass filter to knock out those frequencies if you want to listen to 2 meter FM with the SDR. Good quality cables can be useful. You don't want something that's going to be RF noisy, and computer cables can do that occasionally. Faster computers are better, but it really depends on how much bandwidth you're going to need. And I'm going to show you a demo on both a Windows computer that significantly more power than we need, but I'm also going to show you a demo using a Raspberry Pi, which is, and it's an older Raspberry Pi, a 3B, which doesn't have a lot of horsepower, but it's adequate to receive some signals and process some signals. So this is where we get into just a little bit of technical stuff, but it isn't too bad. So I mentioned, what happened? That did that without even moving the mouse. So I mentioned earlier, SDRs utilize digital signal processing, often performed by a field programmable gate array, the FPGA. That's just a highly capable digital processing unit that was really the crux of why we can do SDR today. It's based on, and I'll tell you what, let me check real quick if we got questions. No, Stephen, you've posted where to find some of these devices. Good, thank you. The Nyquist sampling theorem. This is, in a nutshell, in order to digitize a complex signal, you have to sample it at least twice the speed or twice the frequency of the highest frequency of interest in that waveform. So for example, just simple, if you want to process a 100 kilohertz carrier with a 1 hertz or 100 hertz oscillation or AM a modulation on it, you would have to sample in order to reproduce that signal at 100 kilohertz plus 100 hertz. So if you sample at a lower speed than that, you can end up with artifacts that corrupt the signal that you're decoding. It just 2 times the frequency. So if we're, think about 2 meter FM, roughly 146 megahertz, you have to sample at twice that rate, which would be 292 megahertz. So the reason that SDRs have only recently become popular in these to be used in these bands is that the integrated circuits needed to be fast enough. Years ago, they could do it, but they were very, very expensive. And now the hardware, in order to do this processing, is a lot more economical. That sampling is done with an analog to digital converter, an ADC. And again, that as I mentioned, the direct conversion didn't become practical until those sampling speeds increased a lot. Early days, the signal processing was done at IF frequencies. So when the hardware was slower, your first stage would be an RF amplifier and then a mixer to drop the your baseband down into an IF frequency, and you could run slower hardware. We don't have to do that today. So here's a simple block diagram of the Rtl Sdr that we're going to fool around with tonight. Low noise amplifier, an RF filter. So there may be some components at the in the hardware just to filter out spurious or undesirable frequencies. This one is not a direct conversion. There's a 28.8 megahertz oscillator that's dropping the baseband now down into an IF. We run that into in the lower block where the processing begins. Oh, the VGA, that's a variable gain amplifier. That runs into the processing chip into the analog to digital converter. Coming out of that, you see 2 mixers. There is a one's labeled sine, one's labeled cosine. That's really important, because if you've read anything about SDRs, you've probably heard something about the IQ signal. And this is where the IQ signals are created. On the cosine side, and I'll explain why it's called the cosine side, is the I signal, which stands for in phase. This is just a reproduction of the incoming frequency. The sine side is the Q, and it's phase shifted plus 90 degrees. And this is how the magic happens. So we're going to go into this just a little bit. Then you see the IQ going into a USB control, and then that's what plugs into the PC. But these IQ signals are the real key. So I was trying to figure out a representation of how to illustrate this. But if you remember from high school trigonometry, the cosine of this phasor here on the lower left that's horizontal, this represents 0 degrees. The cosine of that phasor, that vector, is 1. We normalize these signals to 1. So as they go around the phase circle, noted by this arrow here, omega, at 0 degrees, a cosine is 1. This doesn't represent a sine wave. It represents a lagging wave, but a sine wave compared to the cosine wave would be lagging by 90 degrees. So it would be directed straight down, its value at the time when the cosine wave is 1, the sine wave is 0. As you move 90 degrees, or if you move 45 degrees, actually I can show this. I'm going to jump ahead. The blue is the cosine wave. 45 degrees later, the two values are equal because the lagging one has been rising, the cosine wave has been falling. And this value, both of their values are 0.707. At 90 degrees, the cosine goes to 0 and the sine goes to 1. So this is, again, magical, because this is what the digital signal processor is actually processing. It doesn't matter if the input signal phase is varying. It's always defined as being 90 degrees ahead of the Q signal. But what happens is that when you put the value of it from that phasor, from the value of those curves, you now have numbers, just pure numbers. You don't have to worry about degrees of the phase. You don't have to worry about the changing frequency and different modulation, because you can all handle this mathematically. And to demodulate that signal coming in for an AM signal, where think of x of the function x of t, that's simply the audio that you're demodulating. And if you take the square of the value of the I signal plus the square of the value of the Q signal, the square root of that, if you remember the Pythagorean theorem, which happens when you're figuring out values of phasors with different angles here, that's how you demodulate it. For single sideband, you don't even have to worry about that. The I signal is the audio at this point. The value of that cosine wave is the single sideband signal demodulated. We get into FM. Yeah, this takes a little bit more math in that digital signal processor to do it, but it's pretty easy when you program that. And then phase modulation is simpler than phase modulation. But I'm going to give an example of this AM modulation. If we go back to this signal, at this point, the I signal is 1. I squared, or 1 squared is 1, plus Q, which is 0, squared is 1. The square root of 1 is 1. And that's the value of the demodulation at that point. If you go to here, 0.707 squared is 0.5. You do that twice, you have 1. The square root of 1 is 1. If you go down here, it's just reverse. The Q signal is 1. The I signal is 0. There's no modulation on this. All you have is a steady state signal with a value of 1. If you modulate this, by the time you get to this point, or I should say at 45 degrees, if there was some modulation on it, the red signal would be at 0.707, but the blue signal would either be above that or below that. And that's where the AM modulation is detected. This is SDR in a nutshell. That's how this works. So I don't think we have to go any deeper than that, because it's mathematically it's beyond me. But this was the simplest thing I could find that explained why that IQ signal is the key for an SDR. Any questions? Before that's actually the end of the lecture. After this, we're going to play. But anything It was either boring or easy or over your head. Just let me know, because I might want to refine this if we do this for some other folks. So your feedback would be welcome, and you may be brutal. You have permission.
I'm not going to be brutal at all. I think this is interesting. Did I step on someone?
Sorry, I had my radio on.
Okay, this is Heidi, K0HID. This is might finally bring into perspective a lot of things I learned when I was in college a million years ago, and make it practical. The one bit I missed, and maybe it's because I missed some of the regular club meetings, is what do we want this for? What is SDR useful for?
Well, that's what I hope to show you, because are you familiar with Web SDR, where you can go on the internet and find a website where an SDR is running and tune the ham bands?
I am not. That's why I say I'm really, really ignorant about all of this, but it sounds really interesting, because I am.
You know, we can probably try that. Yeah, we can probably try that, because one of the things that I'm hoping to show you tonight with my Raspberry Pi is a very, very simplified version of what can be done. So I'll give you a practical example. I could set up a Web SDR and monitor it over the internet from while I'm upstairs watching TV, and I can essentially see the entire 2-meter spectrum. And I can, without having my radio with me, I could watch where signals start popping up and know what repeaters just went active. And I wouldn't have to hold the handy-talkie with me, have it with me scanning all of those frequencies. I could get a visual. That's
brilliant.
So that's just one simple example. The other thing is that I'm using an SDR. I've got one running in my attic right now that is listening to the ADS-B signals from aircraft that are flying around. And I'm feeding that to FlightAware. So FlightAware has this network of thousands of feeders that are just listening to the aircraft transponders and getting their altitude, their speed, and their position all reported to them. And that's why FlightAware can give you such accurate information of where aircraft are anywhere in the world. So I had my business partner and I had a fun conversation about this. One of the aircraft that doesn't report that information is Air Force One. But you can actually track where Air Force One is flying, because you find out where other aircraft aren't. So you can see if they're flying through a air traffic routing. All of a sudden you'll see a separation of aircraft, and you may not get an exact position, but you know where it is roughly. So that's an SDR that's running 24/7 in my attic. And I hadn't thought about pulling up my screen of that. I might see if we can do that a little bit later and see how much time we've got. But
yeah, I think that what you just described is brilliant. It just really explains to me why I'd ever want to try to investigate this stuff. And I really like this idea. Thank you.
One of the other things, and I mentioned, is that you can build relatively inexpensive equipment. Now, if you do with an SDR transmitter, it would be relatively low power, but it would be a pretty simple thing. You bring your iPad and a Raspberry Pi and an SDR and go do SOTA or POTA activations with very inexpensive gear. So it's not for everyone, and not everyone is going to find practicality in these, but they're very, very capable receivers.
But didn't you earlier say that most of this is done as receiver only? You lost me with it, that it's going to be transmitting.
Most of it is, unless you're buying commercial equipment.
Okay.
That's utilizing SDR, because it's more complicated to do the transmit. It can be done. I would rather master doing some of this stuff a little bit, and you'll see why it's not just push a button and the application's going to work here. So let's see if we can move on.
Hey, Loren, let me add to that a little bit, if you can hear me.
Yeah, John.
One of the things a group of mine did in California is basically you tie two SDRs together and you can unlock the trunks that the police use for their 800 and 900 megahertz transmissions, because one SDR was used to actually link up to the control signals, and the other one was used to decode the signals once they found it.
Yes.
As long as it wasn't encrypted.
That is another thing that can be done. The ISM bands, you can monitor, there's probably some nefarious things that you can do with this stuff too, that we probably don't need to talk about. But they basically give you the opportunity to go explore the spectrum and see. DC to daylight is the term we used to use. It's that if there are signals in there with an SDR, you can see them. You can't necessarily demodulate them because a codec requires, like a mobile phone. We could look at mobile phone signals, but we would have to have the codec, the coder decoder for the digital signals in them to actually make sense of them. But again, if you're tracking down RFI, this would be a very simple receiver to go utilize to go find out, which power pole transformer is arcing and spewing out RFI in your neighborhood as a possibility. So it's a receiver. Think about it as that, and then with a little more complication, you can make it into a transmitter.
Loren, if I may interrupt.
Yes.
Should you have the need, I have a web browser here showing my FlightAware system. I do the same thing.
That's right. We talked about that a while back.
Yes.
Yeah. Let's do that a little bit later. That'll save me from tracking it down.
You bet.
Thanks. So we're going to talk about SDR Sharp right now. So we're going to be I've got an Rtl Sdr plugged into a USB port on my desktop that's right beside my left knee. And the SDR Sharp, it was written initially for the AirSpy SDR unit. So I think I showed a picture of an AirSpy on an earlier page. But obviously, it doesn't need an AirSpy SDR because it works with the Rtl Sdr. Now, this took me a little while to get it to work, but I downloaded the software. You have to install the drivers because when you plug in the USB, Windows loads a driver that does not work with the dongle, and you have to go through some procedures, but there is a YouTube video, and I've got a link to it here that will show you exactly what I went through to do it. But when you install the Rtl Sdr .bat up here, it installs this SDR they misspelled it, SRDLL file, and this app called Zadig.exe. This Zadig is an application that you can use to replace a driver in your system. Takes a little while to get through all of this, but it works. And here is a screen capture of this working, and I did it for an FM broadcast receiver. So at this point, I'm going to bring up that software, and we'll see if we can get this to work. I'm going to take it down to broadcast band, and I'm going to be Steve and I were talking about this a little bit. Since it's being recorded, we have to be a little careful about commercial use of music. So I'm going to start this up and probably mute it here fairly quickly. So that's 98.1 FM. And let's see who this is. That's 98.9, and we'll go up to, there's 99.9. So what's really kind of interesting is that we can see the spectrum. So I can expand this out, and we've got here, let's look at the width. That's 100 kilohertz. So this is a 200 kilohertz wide signal that
By the way, we're not getting your audio, so you're safe so far.
What? Oh, no. I thought we tried that the last time.
We did.
Well, I apologize for that. So what I can tell you is that I was listening to some music, and this was talk radio on this channel, and we go over here. I'm going to go down.
We still have, Loren, do we still have any FM stations that are mono only, not stereo? Because they would look different, I suspect.
Well, what I was going to show, what is the local public radio? 91.95.
91.5.
I'm not getting that in. But one of the things that I have seen is some of them have subbands, subchannels.
Yes.
So you see the FM signal, the primary one, but then off to the side, you'll see some lower fidelity subchannels that are being broadcast as well. That signal we saw a while up here a little further. Let's see if we can. There was a spike coming up on one of these channels, and that is some of the digital information that's being sent. I can't remember what it's called, but when you get the channel, the name of the song scrolling as well, that's a digital signal that's embedded into this, and you can sometimes see that on these. So I'm going to go up here. So Tim, are you able to give a call on the N0 NLX
XLF
repeater?
I am. I have a radio beside me. Let me get set up.
So I'm on 147.075, which is the repeater we use for our weekly nets. And I'm hoping that we actually see two signals pop up. Let's see, 600. Actually, let's go back here. So we should see the repeater signal right here at 147.075, and then 600 kilohertz up, we should see Tim's actual transmission, because he's just down the hill about 1.5 miles from me.
All right. Are you guys ready?
Yeah, go ahead and do a test call. I'm not going to respond. I don't have a transmitter here because I'm using the antenna for just the receiver. But
Right.
let's see if we can see him.
Okay. What I should mute my Zoom call. Yeah.
No, I don't think you have to. If you're not hearing the audio from this end,
Okay.
we should just see the signal pop up. So just, oh, there it is. There, you just saw on the waveform here.
This is W0TLM using this repeater for a short test. This test is part of a class demonstration on SDRs put on by the W0TLM Amateur Radio Club. I ask that no stations respond to this test. If interested, please check out the club's website, W0TLM.com. This is W0TLM clearing this frequency.
There, your signal went down right there, and then the repeater lagged a little bit. So that obviously worked. Now, I didn't have the audio turned up here. It wouldn't have made any difference. I would have only heard it, but at least visually, hey, the first demo worked.
Right.
Yeah.
No,
So Loren, you can record off of this, right?
Yes.
So this is the part where I'm supposed to stimulate a whole bunch of interest, and you guys can go play, because I haven't gotten that far myself. I was spending too much time playing with a bunch of different ones that I never really got too deep into it. But yes, that would be the case.
Now, it's one of the things that's fascinating is you're going to get to GNU Radio later, right?
Yes, I am.
Radio. Okay. I just want to give you a heads up about that. Since you're watching a wide area of this frequency band, you could imagine that you could put filters side by side, bandpass filters side by side, and separate out individual channels. GNU Radio then would allow you to put decoders on each of those channels and decode them all simultaneously.
I was hoping to show you that you can find a bunch of these decoders in here for exactly that. So
one of the reasons I mentioned that is I'm involved. I wrote some software for a ground station for high-powered rocket telemetry. And they do 10 channels side by side. And so one of the things they always wanted to do was put up a large display at the rocket launch sites and listen to all the channels simultaneously and see which rockets are sending what telemetry and be able to watch them all simultaneously. And GNU Radio would be the technique that they'd be using to do that, and a single Raspberry Pi with a single receiver.
That absolutely. No problem, John. Gotcha. If you go back to one of the earlier slides that I showed about, whether the computers are powerful enough, when you start adding a bunch of those channels, you're starting to use resources, and the Raspberry Pi will have limitations before some of the other the other ones do.
Correct.
But that you're absolutely right about being able to split that out, and we'll get to that here in just a second. Actually, that's kind of next on my list. So
the other thing you were showing there, Loren, was the spectrum going down to an AM band looks very different than the FM.
oh yes, it would. I didn't think of doing that, but well, let's try that.
Something like 1460 maybe, or I don't know. I'm just looking at channels in the Colorado Springs area. I know nothing about what they are. 1530 is another one. Country
740 is one of the talk radio.
There you go.
850 is, I'm not seeing anything. Now, I did not click on AM here. It was smart enough to know that I was tuning in the AM band, just like it knew that in the commercial FM band, we could listen to, it was a wideband FM. And when I went into the 2 meter band, it went to a narrowband FM.
Mm-hmm.
So I'm not seeing any AM, but the antenna that I've got up on the roof is a 2 meter, 75 centimeter antenna.
That's a good reason why.
So that might have some limitation here.
Also, some programs or devices have filters that lock out AM unless you deactivate it.
Which is some of that RF filtering at the front end, because they typically are the low power or the high power stations that wipe out the whole band, because they just they swamp the receiver. So yeah, that could very well be the case in this particular one. So let's see what else. I just took a couple of screenshots to include in the presentation. GNU Radio is next. This isn't going to be a great demo, but I want to show you what you can do when you start to understand how the signal processing works. So GNU Radio is a software radio ecosystem. It's written in Python. It's all open source, but what it does is it's a software development toolkit with signal processing blocks that are, I'm going to show you the GUI, the graphical user interface, that you use to put together a radio. You actually build a radio with the building blocks. Some key links here, both on, here's the Willem Schroeder presentation that I based this on, and some YouTube videos about how to get it working. I've got a couple of links in here that describe what it is. Because it was Python, because it's primarily a development toolkit, it's really the people that are serious about it are typically Linux users, and somebody has built an executable that you can download and install to get it to run on Windows. It would be, if you're a Linux person, it'd probably be a lot easier to do it on a Linux platform, but it does work. So that receiver, the application, now this is what you build. So here's a 2 meter narrowband FM receiver. Here's the RTL interface over here on the left. There's a low pass filter, a squelch, a demodulator. Actually, they call it a modulator, but it demodulates. And the audio sync. I'm not sure why they call it a sync, but this is what you need to actually hear the audio coming out of it. And you piece these together, and nothing is read on this screen, which means all of the connections that I've made and chosen are okay. If you've got, for example, there's a sample rate here of 1 megahertz. So we're taking 1 million samples per second. If you start putting numbers in here that are off, and they're not compatible, it won't work. You can't even run it. So to Heidi's question on usability earlier, this GUI essentially creates a Python code script. And that Python script, if you've got the Python compiler in your computer, you can run the code. You don't need to bring up the application. You've actually created the application that runs. So this could be embedded into some kind of a product. It could be embedded into a computer that maybe you're using that will develop, to develop a specific application. Again, if you're, it's a bad example of taking it out in the field because you don't have the transmitter, but GNU Radio has the capability to build a transmitter as well. So your computer could become both the receiver and transmitter. And I might have a diagram that shows that. I don't remember if I put that in here or not. So let's bring up. Here is another wideband FM broadcast receiver. So here's my Rtl Sdr. I set a variable up here, a 2 million samples per second. I'm running into a low pass filter where I'm doing what's called decimation. Decimation is essentially dividing by a number so that when we're processing later on, we're not processing every sample. In this case, we're processing every 8th sample, and we get enough fidelity out of that. You have to sample at a higher rate than when you decimate, that if you remember Nyquist's theorem from the beginning of the presentation, you need to have the samples, but then you can start to whittle it down because you've captured signals that that won't give you problems. Then we have a wideband FM receive demodulator. We're resampling, which is another decimation to get this down into an audio baseband. This multiply construction or construct is a volume control, and here's the audio. So I've got a module in here that if I didn't have this, I would just program an audio and I'd end up having to turn the knob on my speaker, but I'll show you how this works. We execute, and now notice the code begins to run in here. It's essentially, I don't know if the right word would be compiling, but it's certainly running through these modules and figuring out what it needs to do with the signal that's inbound. Why didn't it start?
It can't get to the Rtl Sdr, it looks like.
Failed to open RTL device. Okay, it may be because
You left it running.
I left the other one running. So let's do this again. One more time, execute. We'll go through that process again. It found that so I don't know if you heard that. I take it you didn't.
No.
You did not hear the audio. Well, now I lose the impact. I built a chooser, I put in a chooser and I programmed in 2 stations. So when I click this, I get a different station. I could program a whole list of FM stations that I wanted to listen to. So now this is hands-on. This takes a while to figure out, and I will be the first to claim that I'm not proficient at all, and I don't really understand what all of these are. But if you're interested in playing, this is the tool, because over here, take a look at the blocks, the module blocks. So just within audio, here are a bunch of different decoders. So if you've got, I guess, actually, I'm not sure what the audio decoders are actually going to do. You've got math operations that can be performed if you're doing working on complex complex math. Phasers have real and imaginary parts, and this is what you would use to detect it. Here's modulators, AMD mod, FM, GFSK, GMSK, narrowband FM, phase modulation, quadrature demodulation, wideband FM. So it's got, if you remember that chart where I showed you the math of how to do it, they've programmed in all of these different types of modulation schemes, and you just you pick what you want to do.
So, Loren, describe the hardware from antenna to this screen that you have in place.
Okay, I'm gonna tell you what, let me stop sharing for just a second, and I'll give you a tour of my ham shack. So let's take the blur off. When we talk about shack, yeah, I'm in the basement shack. So up there where you see that insulation, I have a cable chase that goes from the basement up into the attic of my home. And the coaxes are over here coming down the wall. You see a headphones hanging, but the coaxes are coming down in here. Here's my FTDX 3000. And here's the coax, and there's a small piece of coax running down to the computer. And there's the Rtl Sdr, and then Steven's holding one up there. It's got a SMA connector on one end. He's got the protective cap on it, and then a USB connector, and that's the extent of the hardware. And that's antenna to hardware.
My point in mentioning that is that everything else you did with the boxes in that GUI transformed this piece of hardware, which can listen to anything along that entire band, into a 2-channel FM radio, just by dragging those boxes into place.
Yes, exactly.
And you can do that with pretty much any kind of signal that you want to receive.
Right. So over here, I'm going to double click on the properties of that. And I didn't use all of them, but here's where we programmed in sample rate. And the variable name is samp_rate. And up here, I defined the variable. Let's close that. There's where I plugged in the variable, 2 million, which I could have put into engineering notation and called it 2E6, and it would have been the same thing, 2 followed by 6 zeros. but we also deal with setting the channel 0 frequency to tuner. And my tuner was set up here in this chooser, it was called, and I programmed in option 0 as 98.1 and option 1 is 99.0. So this chooser is what brought up the little box that gave me radio buttons to push, and it also included the volume adjustment that I have here. Plugged in a low pass filter with a cutoff frequency of 100 kilohertz. So we have choices on the type of filter that we're using, and these have probably different roll-offs. Some of them have more ripple through the baseband, but these are mathematical representations of different types of filters here. Here's my wideband FM demodulator. The down rate here was set by this variable down rate. So this basically resamples, or this determines the bandwidth of the actual demodulator, which would be chosen based on the bandwidth of the signal. And then again, I mentioned earlier about the volume control and adding in the audio. So I wasn't able to figure out all of this. Let's see. Let's go down here to type in GUI. So there are widgets that can be added, and this QT GUI frequency sync would have, if I had been able to figure out how to make it work, as soon as I dragged this over and tried to make it work, it's a fast Fourier transform, which takes a frequency domain signal and converts it to a time domain signal, which is what you see on those images where you saw the signal. That was in the time domain, and this is what creates that display. I know that works because I've seen people that have done it on YouTube, and I've seen examples of it. I wasn't able to figure it out. That was, I spent a couple hours on it this week, but no success yet.
Do you see a waterfall sync?
Well, that
one might be easier to use than the frequency sync.
Here's a waterfall sync.
Yeah, take that out of your SDR source.
Let's try that. Let's see what happens. Let's kill that. Okay, execute.
My point being is that I happened to look at the Wikipedia page, and it's showing exactly the configuration that you just created as supposed to be able to show a waterfall. But of course, you're going to have to set frequency and bandwidth to what you think it should be. But
well, it's got a 2 meg default bandwidth here.
And your center frequency is 0 currently.
And yeah. So every time I've hooked something up to here, the radio doesn't work. So,
interesting.
Yeah. So anyway, it would be something like that to build a display so that you could see where you're tuning. Take a look at the signals like we did on the previous one. I'm going to shut this down because I want to have time to show you something else here. And what I need to do is I need to pull my radio out and plug it into my Raspberry Pi. We've been 2 for 2 on the demos. Let's see if we can go 3 for 3.
So you move the Rtl Sdr over to the Raspberry Pi.
Yep.
Okay.
So there it is right now. I don't know if you can hear it. I've got a fan that's going out. I 3D printed and mounted a fan in here to keep it cool. And it's making noise.
Can't hear it.
Good. I'll be annoyed by myself then with it. So now, here's the interesting thing, and this is what's great about this particular application. Let's go back to here for just a second. So this is Linux-based. Run it on a Raspberry Pi. We get to look at it on my screen share on a Windows computer because it's operating as a web server, and I'm going to pull it up on my network, and we're going to look at it from the Windows computer through my router back into the Raspberry Pi. And let's see, what have we got next? I'll avoid that one for just a second. So let's bring up this 192.168.46.239. And now that is being provided by the Raspberry Pi. So we're now accessing the Raspberry Pi. This is what I was talking about. Did I?
Or maybe
I need to share the screen. I'll bet that would help. So this is its IP address on my home network. And I'm looking at it, as I said, on my Windows computer, but I could just as easily be doing this from an iPad upstairs. So what I've done is there is a settings button up here. But let me back up just a second. In order to get this running on the Raspberry Pi, all I had to do was download an image off the internet, flash a SD card, a micro SD card, plug it into the Raspberry Pi, and I have this. You don't need to know anything about Linux. You don't need to know anything about programming Raspberry Pis because this does it all for you. So we go into the settings, admin, password. We have now, again, from my Windows machine, I can set this up. So I've created profiles for SDR, Rtl Sdr user USB stick. I'm listening to 70 centimeter repeaters, 2 meter. I programmed 2 channels really, one at 145 megahertz, one at 147 megahertz, broadcast FM and airborne communications. So broadcast FM, you make a few settings, you set sample rate, you pick your initial frequency, you pick your initial modulation. Now, when I go back here to select my broadcast FM, here comes the radio signals. And once again,
when you did the share for your screen, was there an audio button on the share?
I've never seen an audio button on the share.
So I think we have some problems with trying to share YouTube that way from other calls I've done.
So it worked when it was just the two of us. I wonder if that has anything to do with it.
It shouldn't. It's just the source.
So anyway, I'm seeing a portion of the spectrum. Now, I haven't quite figured out here how to change the width. It probably has something to do with the sample rate, but gives you an example. I'm going to bring up 2 meter. Here's my 145. I've got it tuned so it opens up on the Colorado connection repeater, 145.13.
If I may interrupt, it says when you click on the share screen, there's a share sound button on the bottom left corner of the share window, share dialog.
Well, let's stop for a second.
Do it one more time and see if that works.
Share screen, share. There it is. Share sound. All right, let's go back here and you can actually, hopefully.
Approval plus the most cash ever for your trade. The big used tent to
It worked.
Motor City. Experience Phil Wong and drive Colorado. See dealer for details.
That's how I feel right now.
So obviously
Now we're never going to hear Loren again.
So yeah, I was actually hearing things when we were doing this the whole time. I'd never noticed that button before.
Now we know.
So let's go back because we have no copyright issues here.
So just tune to anything. I was trying to get you AM. I can run 40 watts on this, but I don't think you got me either.
So that's a Colorado connection.
Yeah, that's a next. With N9NJS here, but not in Chicago. This is KF0IIM here, but not in Minneapolis. Clear off of American Point for the time being.
This is an interesting. I don't know where this signal is coming from, but this is a repeater that's been linked in from. It must be networked around the country because I've listened to Australians on this. I've listened to people from all over the US. It's coming in at 146.415, I think is the frequency.
Who just appeared there?
So anyway, back to 1.3.
With a handheld isn't doing me any favors either. I'd be interested sometime to try base to base.
So Heidi, this is what I was mentioning. You can see, this is probably over here on the right side, a repeater ID that occurred. And then let's look at my 147. There's something there. Well, that's probably the tail end of an ID. So, Tim, if you broadcast again, we would see you popping up on here. Want to give that a try again? Let me tune to 075.
This is W0TLM and 0XLF repeater 20.
Okay. One more time, Tim, if you would.
There was a lot of feedback. I don't know if you guys heard that part or not when I did transmit. I don't know why that is.
I did not hear. I heard you coming on Zoom in the microphone.
That was me. Sorry, I have my radio on too, so I'm muting myself now so you can try it again.
Okay.
This is W0TLM testing.
Gotcha. Yep. So, Tim, you broke squelch. I set that up so we weren't listening. You know, we're not listening to the static, and you broke squelch, and there you were. And oh, by the way, here's your transmission. So I was hearing both of you. I could have listened on either frequency. So that was good. It worked.
So you could make that display wider so you could see more of the signal and its characteristics.
Yes. Yeah. And I think if we go back here, so if we look at the 147, the initial frequency sample rate, there are other settings. Waterfall levels.
No.
So the answer is a definite maybe. I'm pretty sure you can, and I think it has to do with how many samples you're setting this at. Let's try something here. Let's go to 4.096 megahertz. Apply and save. We'll go back here.
4 for anybody local in the Springs.
So that just changed the bandwidth that's showing up here, because now it goes from 146 up to 148, and it about doubled the bandwidth that's being shown in here. So yes, there are ways to do that.
You want me to run a test again just to see if it changed?
Yeah, go ahead.
Okay, let me mute.
Let me put the audio in. Set the squelch.
This is W0TLM testing.
There you are. So the squelch tail out here, and that was your actual transmitter that shut off exactly when you went off the push to talk. So, yeah. Let's see, what else have I got going here? Let's see if there's any airborne. So 122.1, I think, is 122.2 is FAA regional air control. 124 is Colorado Springs approach, and 119.9 is tower. So I'm not able to change the frequency outside this passband. So anyway, I was listening to some aircraft on approach into Colorado Springs the other day. This is AM. Oh, the other thing I was going to show you is that you can actually do DRM or free DV demodulators or codecs are available here. So you could listen to if a repeater is doing digital radio, you can actually decode that with this particular SDR software. I'm going to open it up for questions because we are almost at 8:30. I have one more thing I could show you, but it's the last thing is I'm using an SDR play to control my HF rig. I bring up an application where I'm able to look at the entire band and the waterfall. It's a pan adapter equivalent, but I can use the SDR that will send a frequency, what frequency it's on, to the transceiver and change operating frequency. So I can tune to a signal very, very quickly and contact them. Or I can use the waterfall to find a free area if I'm going to call CQ. Let's see. Basically, that's what it looks like. I'm still sharing, I guess. So here's the 20 meter band. I can tune the frequency here, or I can just click on the screen. And for Heidi's benefit, that's how I use an SDR every time I operate in HF. Is I bring this on and use this to tune. So I very, very seldom will use the tuning knob on the radio. I may, I don't listen to this signal typically. It's interesting because if I've got the speaker for the radio on and the speaker for the SDR on, there's a lag for the SDR. It comes in a little bit late. But I could, I've got lots of filtering options when I use the SDR. So if I was having issues with interference, I probably could do a better job of filtering with the SDR than I could with the radio itself. So just another piece of software, another piece of kit to integrate together. So what have I talked about and left out? What kind of questions? We've reached the limit of my material. So at this point, it's all ad lib.
And your material has been outstanding. Thank you.
Yeah, I liked it. I do have a question. So since if you're going to use this SDR as a receive only, and so does it matter like the coax that you use for it? Is it, if it's lossy, it probably doesn't matter as much?
So think about it. You would want to do what you do with any other rig. So any matching differences, I mean, matching is less important. Receiving, it's not totally unimportant, but it's less important when you're trying to run high power through it. So matching, but if it's a lousy, if it's a lousy coax, yeah, it will affect it. If it affects your normal rig, I say normal, your whatever you're using today. If you wouldn't put it on that, you probably wouldn't want to put it on your SDR.
Okay.
That said, I used to run a receiver with basically a coat hanger. And if you can hear it, you can listen to it. So, the joke is with a good tuner, you could load up a picket fence or a bicycle and use it as an antenna. So
Rain gutters.
Rain gutters, window screens. Yeah, so the laws of physics still apply, and you could do what you can get away with.
So I have another question. This is regarding, okay, using your SDR as a receiver, and tried to use the same antenna for that and transmitting on your normal rig?
You would absolutely need a TR switch, because if you don't, you're going to blow that SDR right out of you're going to blow it up. You'll get to do that for about a microsecond, and then the SDR won't work anymore. So what you do is you need to have a high-speed switch that's timed so that when you hit the push to talk, that thing is instantly isolated from the transmit path.
I'm going to pull up the one I'm using. MFJ makes one specifically for SDRs.
Yep. That would be, if you're gonna use this. Now, I don't need to use that with the SDR play that I'm using, because my Yaesu rig has that TR switch inside, and it shuts off the feed into the SDR before it transmits, before it applies power. So the answer is yes, you can, Tim, but you got to be careful.
Yeah.
So basically, I have a similar setup to what Loren's doing. I just put the link in chat for the MFJ, and I have I'm able to use my 857 to transmit on HF FT857. I also use the SDR with, depending on what software mix I'm using, as a pan adapter in some cases. And so I'll tune with that, but when I'm transmitting, I block the signal from getting back into the SDR so I don't overload it. And this is the device I use. It's the RF Sense SDR receiver TR switch. And so it gets power, it gets your antenna routed through it, and then the SDR picks its antenna feed from that as well. I also have a dual receiver SDR, so I split and feed both outside of this box. So
I was talking to some of the guys at HRO, and they said you got to be cautious about this if you're doing QRO power, because there's enough energy going through that switch that actually could still damage the SDR. So it's okay for the lower power transceivers we're using, but if you go QRO, you definitely need to be careful.
Yeah, I carefully chose equipment that matches what I can do.
So I'm sharing screen here. This is my, I fired up my FTDX 3000, and 20 meters is active at nighttime. The solar flux index is up around, it was 137 when I looked at it earlier today. We got propagation into the night on 20 meters now. Out of curiosity, I wonder if there's anything on 17. There's a few signals. And again, I'm just clicking on this and it's changing my transceiver. So here's the FT8 over here. So FT8 is very active right now. I'm not seeing, I've got some RFI issues on that I haven't tracked down. I hadn't worried about it so much on the these upper bands, but and 40 was quite active tonight as well. What's
12 meters look like?
Pardon me?
12 meters.
12. I got bands upper 12. So we've got some
FT8 and
CW. Let's see, that might be FT8 here. Yeah, so it looks like there's some activity on FT8.
Yes. And somebody up in the upper band.
I don't think that's an audio signal. Let me.
Okay.
Yeah, I don't hear any modulation on it. I'm just hearing a tone.
Okay.
Oh, here we got something.
915. That's still in the digital band or CW.
Yeah, so I love SDRs. They are just so versatile and find the right use for them. A lot of fun.
So I have another question.
Shoot.
So the SDR Play has like standard one basically, or a couple of them, and then they have a duo. So it has like 2 ports on it. So what would be the advantage of having 2 ports?
Different antennas. So you could have an HF antenna on one and a VHF antenna on the other. One of the ports is also you can power. So if you've got an LNA, a low noise amplifier, which you typically want to mount as close to an antenna as possible, you need to provide power to it. And most of the LNAs have the ability to take power off of the coax, so you don't need to run another cable. And one of the, I think one of the ports on the SDR Play will provide voltage, DC voltage up, to a remote amplifier. So those are that's one of the options I think that you get between the SDR Play, the 1 or the 2. And then they've got some newer versions that I don't really know what they've done. One thing about the SDR Play is that they've got some pretty decent filtering in the front end that helps avoid some of that overload from broadcast stations.
Loren, can I share my screen for a minute?
Sure.
And then what this is you're asking about right, press the share button, Steve. Let's see. Well, fine, I'll give you the whole desktop. This is silly. Okay. In this window here, can you see this? The one that's
in your PyAware behind.
Yeah. Oh, yeah. Well, we'll ignore that for a minute. So this is the PyAware computer, but here's the Duo right here. And I use a splitter and I'm feeding my HF antenna. That way, my point here is I can be watching 2 bands simultaneously because I effectively have 2 SDRs.
Yeah.
And so I use it that way. You really can use it other ways. The SDR Duo is a little bit weaker in the sense that there is not full support, hasn't been for years since it was released, for doing the kinds of things you really want to do with 2 different receivers. And so inevitably you're using one of the receivers with full software control because of that limitation. And so I can run, and so you can see that I have Pi Radio here, that's doing my rig control and running any software I want locally in the Pi, and then I can remote desktop into Pi Radio. And then I have switches and things for my antennas. And the latest need I've had is I have to rearrange the station to add a 7300 to it. And so now I got to figure out what to do with my HF antenna routing. That'll be fun. But anyway, that's that. You were asking about PyAware. Let's bring that forward. This is your FlightAware running on the Pi, a separate Pi. And so this is basically the ADS-B antenna sitting on the roof, just like Loren has. Coax running down here in the back of my shack, and then into the dedicated receiver. And I'll pull this one forward again, because the receiver is basically this thing on the wood right here with the SDR attached to the Raspberry Pi, a filter, and then the coax up to the antenna itself, which looks like that. And its software is plotting this map, and these are currently all the flights in Colorado Springs area and where they're going. So does that make sense?
Yeah.
So thank you, Loren.
I have an interesting view from my lot of where my house is. I can't see any aircraft below about 11,000 feet ASL.
Oh,
So about 4,000 feet to the north. So I see aircraft on approach into Denver, but I can't see them when they're, after they get below about 5,000 feet.
They just drop out. That's wild.
But I have a view to the south, and I can detect aircraft south of not Lubbock. I-40 runs through
Albuquerque.
No, in Texas, in the
Amarillo.
Amarillo. I can see aircraft south of Amarillo. It's almost 300 nautical miles from here.
That's wild.
So I've got a really good antenna, but I've got granite on three sides of me that prevent. So if you guys that live up north have up on the Palmer Divide are in a great place to do flight aware.
It's kind of fun. So flight aware is crowdsourced, meaning that all of us with antennas are hearing what we hear locally. And all of that is reported back to central servers and then distributed to everybody else. And so that's how we all get different pictures of what's going on. And so every time I travel, I turn my gear off and then I get email that says, "Where'd your receiver go?" It's going off the air. I said, "Yeah, I know. Bye."
I just let it run. I had trouble with it for a while, but now it's been running for months without touching it. So I personally feel pretty good about the questions and interest, guys. I appreciate it a great deal. By the way, Stephen, you can probably stop recording.
Okay.